Hello everyone. Today we talk about the collision detection for the autonomous vehicle. This interesting topic. I just briefly introduction the principle how to calculate time to collision between the two cars. Okay, you can apply for the robots. If you had the time to researching and apply the algorithm for the robots, I think it's work well too. The collision detection problem called CAS, they apply for the autonomous vehicle or for the autonomous brake system for the car vehicle. It is the active safety feature that warns driver or even trigger the brake in the event of the imminent collisions with an object in the path of the driving. If the preceding vehicle is present, the CAS continuously estimates the time collision, okay? Time collision TTC, okay? When the TTC time collision falls below the threshold value, so the CAS can decide either one driver of the danger or depending on the system, apply vehicle brakes autonomously. Something like this. It's really easy to understand. You can the car, yellow car right here, they have the time, they have the system collision avoiding system right here, and we have another car on the road right here, the green car right here. At the time t equals 0, we have the distance d0, okay. But sometimes what happen to the green car right here, they stop right here, and our car right here, the yellow car, is coming. But how he know the time collision between how the limit time, it means threshold of the collision time right here. He know at the time at the distance at time t1 and the distance between two cars d1, the cars right here had to apply brake system and stop the car. Okay, so we calculate the TTC time collision. Okay, time to collision right here. So what the threshold value right here? So we need to calculate. In the traffic scenario, the green vehicle start to reduce the speed, right? Reduce speed at the time t equals 0, with when the yellow vehicle equipped with the collision sensor and take the distance measurement d0. A moment later, at the time t equal 1 right here, right? The green vehicle is considered closer, and a second measurement d1 is taken. The goal now is to compute the remaining TTC time to collision, so the system can warn the driver of a yellow vehicle or trigger the brake autonomously. So to compute the TTC, we need to assume the physical behavior of the preceding vehicle. One assumption could be that relative velocity between the yellow and green vehicle were constant. So this would lead to so-called a constant velocity model (CVM). And we had another situation happen is the constant acceleration. And the second one is always we apply for the commercial car. But to do easy one, you can apply for constant velocity for calculation right here. It means they had two cases right here. We can assume the ring car right here. They do the constant velocity. They don't change the velocity from they stop, something wrong happened right here, and the constant velocity to stop right here. But in the reality, the green car right here, they change the acceleration, right? So we had two situations for calculation. But to its symbol, I think we can apply the constant velocity for the green car to practice for learning. Okay. In the physics, you already know the distance after delta t equal the distance time t minus 2 the distance after delta t. It means right? You know the distance up that how far from yellow car to green car at time t equal 1. Okay, it means after the green car move delta t, okay, from here to here, we had to minus this one at time t0 minus the distance from here to here, right, to get the d1. In this case, we say the constant velocity, but in another case, you already know in the physics, constant acceleration, they have this the small part right here, the impact by acceleration right here. So you have the distance at time t plus delta t equal time dt minus delta t minus this part by the acceleration, right? And thus you will have to know we have two model, okay. Because in the dynamic, the traffic situation where the vehicle is braking hard, so the constant velocity model is not accurate enough. However, as the relative velocity between the both vehicle changes between the measurements, so you can see right here the increase in velocity from right now. It's not constant velocity right now. They have the constant acceleration, right? The velocity may be changed after t0, t1, and t2. So we have a different model. This model is refers constant acceleration model CAM. It's different than constant velocity CVM, right? It's commonly used for commercial available collision detection system. So how about the math behind the time to collision? So following right here, we assume that our system equipped vehicle use Lidar. We use Lidar right here to take the distance measurement on the preceding vehicle. The sensor in these scenarios will give us the distance to the closest one right here or here, right? As 3D points are in the path driving. The closest point is indicated by the red light emanating from the LiDAR sensor on the top of the CS vehicle. We put it on the LiDAR sensor on the top vehicle, and when they're scanning, they got the closest point right here on the bumper of the car right here. So based on the model constant velocity we discussed, so we can the velocity v0 can compute from two successive LiDAR measurements. Okay, rely on the formula above. We can see the distance after delta t equal distance after time t minus the distance right here after delta t, right? You use this formula, you calculate the v0, okay? Plug it in formula, okay? You can easily calculate data. At the distance at delta t equal d0. At the distance after delta t, it means the d1. Right here, you see? And delta t right here, you divide, you can calculate the velocity v0. So what the time to collision? The time to collision from here to here at a d1 is mean d1, okay, divide to v0, right? So we already have the v0 right here. You plug it in right here and you plug into formula. You have the time to collision. If we know the d0 and d1 from the LiDAR sensor, we can calculate time to collision. So relative velocity v0 is known. The time to collision easily computed by dividing the remaining distance between the both vehicle, right? So given a LiDAR sensor, we able to take the precise distance measurement. A system for the time to collision estimation can be developed based on the CVM and on the set equation above. Right here, we can see the data point, 3D data point right here. They overlay onto the image of the camera in the highway scenario. They overlay over the camera image. The distance to the sensor is color coded. Green is far, red is close. So you can see right here the color data point onto the image camera. As we can see, the LiDAR sensor provides measurements on the vehicles as well as on the road surface. The cover right here on the road surface too. Some 3D points in the camera image do not seem accurate when compared to their surrounding neighbors, especially the points near the roof of the preceding vehicle differ in the color from the point in the tailgate. The measurement accuracy is correlated to the amount of light reflected from the object, so it makes sense to consider reflectiveness R of each LiDAR point, which can access into the in addition to the XYZ coordinate. So in the LiDAR points right now, we not only get the XYZ coordinate, we had to get the value intensity. It means the R reflectiveness. Also, the image right here below highlights the high reflectiveness with green, whereas the region with low reflectiveness so as a red. So as analysis of the associated reflectivity of the data, the point clouds, so thus deviation often occur in regions with reduced reflectiveness. So right here you can see with the intensity color and the overlay onto the image camera, you can see they have the low reflectiveness and high uh, reflectivity. So in order to derive the stable TTC time to collision from the point cloud, two main steps we had to do. Right now we had to remove all the road surface right here, and we only get the high reflectivity right here. So remove measurement with the low reflectivity. We remove all this one, remove the road surface, and we only get the high reflectivity. So, and the result right here, LiDAR points are shown on the top view perspective as image overlay after the filtering. After we filtering, we don't need to the data point on the surface, road surface, right? We only get the main point right here. So after removing the LiDAR points, so it's much easier to derive the distance dt to the preceding vehicle. And in later video, you can see on the code, LiDAR points are the packet into data structure called LiDAR points, and they have the S forward, Y left, and Z up in the matrix coordinates, and the points reflectivity, or we have the R too. The point reflectivity the range from 0 to 1. 1 is mean high reflectivity. In order to compute the TTC time to collision TTC, we need to find the distance to closest LiDAR points in the path of driving. Okay, LiDAR measurement located on the tailgates of the preceding vehicle are measured time T0 is green and T1 is red. Okay, and the distance the vehicle has decreased slightly between two. Right here you can see when the LiDAR point around here, you can see at the time T0 a green one, but at the time T1 is a red one right here. Okay, so we know that the distance to the vehicle decreased from 8 meter to 7 meter between the time T0 and time T1. Here is the simple map for you to compare two models. One, the CVM, constant velocity, and another one, the constant acceleration. In the reality, in the commercial car, the constant acceleration. Why? You can look at it. For example, the car move at the time TDT equal 25 meter and velocity 30 kilometer per hour. It means green car, right? And acceleration, right now they have the constant acceleration right here, 5 meters per second. If we apply to constant velocity, we don't care that's acceleration, then we apply the formula. And we calculate the time to collision, okay? 3 seconds, okay? 3 seconds. It means after 3 seconds two car collide together. But after when we use the same model, if we apply the acceleration 5 meters per second, so we do the same thing. We just put the acceleration part right here. We calculate the time. We got the 1.91 second. You see, really careful, right? We need to use this model for the safety situation. Following the cursor, search for the closest point in the point cloud associated with the T0. And in the T1, in the code, you can see some similar something right here. At the time T0, we have like lighter point right here, and in the point cloud associated with T1, we have current one right here. After finding the distance, the closest point, respectively, okay, the time to collision is computed by on the formula. Here is short code right here. We will see in the whole the completely code later in the next video. How they, but you can see they use the formula we derive right here. Time to collision, okay, equal distance time to delta t, and the difference divide the difference. This formula, right? This formula, they use this formula to get it right. D1 times delta t minus the difference between D0 and D1, okay? How about, that's the first case we use LiDAR to calculate the time collision, okay? Even though LiDAR is reliable sensor, so errors measurements may still occur, as seen in the figure about a small number of points is located behind the tailgate simply without connection to the vehicle. When searching for the closest point, such measurement will pose problem as estimate distance will be too small. So there are ways to avoid such errors by both processing to the point cloud, but there are no guarantees that the problem will never occur in practice. And one different way we measuring the time to collision without the distance, we use the camera. Monocular cameras are able to measure the matrix distance, right? They are passive sensors that rely on the ambient light with reflex of the object into the camera lens. So it is thus not possible to measure runtime of light as LiDAR technology. So to measure distance, a second camera would be needed. So you can see always on the, I think autonomous vehicle right now, you took two cameras for calculation the time to collision. Given two images taken by two carefully aligned cameras at the same time instant, so one would have now located a common point of interest in both images, okay, and then triangulate their distance, use camera geometry and perspective projection. With more advanced CAS products, so with autonomous vehicle, stereo camera has started to disappear from the market due to the package size, to the high price and the high computational loads for the finding corresponding features. So despite those limitations of the mono camera, but let's see if there is a way to compute time to collision without need to measure distance. Let's consider constant velocity model, right? We introduced previous session of the, okay, about the way to replace the metric distance d with something the camera can measure reliability, such as the pixel distance directly onto image plane. it means you can see right here, we can don't rely on the distance right here, this is one. Right now, we have the relationship between the ratio on the image right here, S0, S1, right? The mapping from the the height, the width of the car, and time t and t0 right here. Okay. For example, at time t0, the height right here you can map to the image plane s0. Time t1 you can map the height of the car right here to s1, right? And we have the focal length of the camera right here. This is the pinhole camera, the central camera. So we have the formula relation all the parameters right here, and it's really easy. You can have plug onto the formula where relate projection and distance S1 S0 D1 D0, D1 D0 is the same last scenario, but right here we don't use D1 D0, we use S1 S0, okay, to calculate the time to collision. And you apply the same formula for the constant velocity model. You can calculate time to collision right here. Right now you can see that the time to collision rely on the ratio between the S1 and S0, the height, okay, of the image plane right here, okay. So the time to collision is computed as a ratio remaining distance to the impact, with a D1 as a constant velocity V0. And we can easily see the time to collision now consists of the delta t, S0 and S1. So it's possible to measure the time to collision by observing the relative height or change of the image sensor. The distance measurements are not needed, right? And we can use the mono camera to estimate time to collision by observing channel of relative height, right? Different lidar that rely on the D0, D1, okay, but the camera right now they use the chain of the ratio between the height of image picture right here. So the problem with the bounding box, we use the neural network, right? You detect the car right here. Neural network has been used to locate the vehicle in successive images of the mono camera, right? For each vehicle, the network returns a bounding box. I think you're familiar with this when you machine learning or deep learning to detect the car right here and return the bounding box and with the width and height, okay? And we can use to compute the height ratio in the TTC equation, time to collision equation, right? Right now you have bounding box of the car and we can apply the ratio of the height, okay, the height of the image right here. You can plug it into formula to get the time to collision, okay? When we observe closely, however, it can be seen that the bounding box do not always reflect the true vehicle dimension, and aspect ratio differs between image, right? Use the bounding box height and width for the time to collision computation would thus lead to significant estimation error. For some time right here in this location is something is not correct. So in most engineering tech, rely on a single measurement and property is not reliable enough. This holds especially true for safety related products. So how we improve this one? We use the test the key points instead. Instead of rely on the detection of the vehicle, okay, we want to analyze its structure on a smaller scale. So if we were able to locate the uniquely identifiable key points, so that could be tracked from the frame to neck, we could use distance between all the key points on the vehicle relative to its order to compute a robust estimate of the height ratio in our TTC equation. Right now, we finding the key point, the feature on the image region right here. And we compare the ratio distance between the two successive frames at time t0 and t1. Here is related distance between the key points in image from 1 to 7. Here the select the key points distance in the picture. You can see the set of the key points has been detected and related distance between the key point from 1 to 7, 1, 2, 3, 4, 5, 7, right? The picture has been computed. So in this picture, you can see 4 key points, 1, 2, 3, 4. Key point have been matching between the successive image, right? And using the higher dimension similarities measure called descriptors. So we can talk later about this. The ratio of all related distance between each order can be you compute the reliable time to collision estimate by replace the ratio S1 to S0 with the mean and median of distance ratio dk factor right here. That is, we in the formula last time we use as the ratio between the S1 and S0. Right now we use the key points feature. We got the ratio between the dk right here to this k right to the prime k right here between two successive frames. And the following right here, you can see related distance between the key points or overlay over the highway driving scene. You can see that. So the next time you can see in the code we'll use the package in the OpenCV called the dmatch or the stroke elements we'll be using in this course and carry idea with some the parameter you will see in the next time, or the matching key points stored in that dynamic list with them passed to the function compute the TTC camera, and they return to time to collision. So here we understand I show you two ways to calculate time to collision for the autonomous vehicle. You can see first one, they use the Lidar to calculate the time collision, and the formula we already know, right? Right here, the time collision, okay. And the second one, we use the monocamera to calculate the time collision right here. Thus, the principle how to build up the collision avoidance system, okay? And see you next video.